exam scheduled for fall. So if your classes begin between 8:30 and 9:59, which ours does, on a Tuesday, Thursday, our exam is on the 9th at 8 a.m. to 9:50 in this room. So do not show up to the, last year it was on a Thursday, and so they had more time. They had a little bit more time. But I'm gonna try to cut some questions out of this exam because it was really long. Yeah. So all exams will be held in the regularly assigned classrooms. The second bullet doesn't apply. And then lab exams, we will not have one, but there will be concepts from the lab reports that will be in the final exam. So stuff like KD value versus decontamination factor, Beer-Lambert law, knowing which one is Lambert, which one is beer. That's probably gonna be on there. All this other stuff doesn't apply. So, yep, here's where we are right here. Let's not put something wrong.
So that means our analytical is on Wednesday, according to the schedule.
Oh, what days do you have?
Monday, Wednesday, 10 o'clock.
Okay, let me see.
It's down. That's Monday, Wednesday, Friday. Monday, Wednesday,
Oh,
10
right
is
here.
the
Okay.
10th.
Yeah, so December, see it the next day from 10 to 11:50. So you guys have like 2 hours, almost 2 hours to take your.
Boom.
I mean, I finished the final in like 45 minutes, so no, I'm just kidding. All right, I'm gonna turn the light back on and turn this off. All right, so we're gonna start at the beginning. If you all have some preferred topic that you would like for me to expound upon, let me know. And I may let you know whether or not it's something you're worried about or not, okay? All right, so radiochemistry and the atom, going back to our very first lecture, knowing the difference between a stable atom and a neutral atom. Stability has everything to do with the nucleus, okay? So protons and neutrons. Neutral atoms have everything to do with the positives and negatives, so that would be your protons and your electrons. So same number of protons and electrons, your atom is neutral, okay? When we're talking about chemistry, like the actual interactions for chemistry, we're talking about the outer shell electrons and how they interact with other atoms and molecules and whatnot. So that has nothing to do with the nucleus interactions. So radiochemistry has everything to do with how the chemistry changes based on what's happening with your radionuclide. With decaying, hey,
Hello.
you're like halfway dressed, buddy.
Yeah, I know. I did it all the way here.
It's okay. All right, I just started. I went over, final exam is up there. It'll be in this classroom. So these are our last dates. So today, this Thursday, and then next Tuesday, if you all feel that you're okay, we can have that class, or we can work on resumes and internship applications. Either way, we can do final exam where I can review till I'm green in the face. But last day of class, this is on a Wednesday, so either way, 25th is our last day of class. So we only have 3 more classes left. All right, so neutral and stable atom. What keeps the atom together? What's pulling it apart or pushing it apart? And also what things you can find on the chart of the nuclides. What kind of information you can find on the chart of the nuclides. Nuclear mass and stability. What do we want to say here? Knowing how to calculate the predicted mass of a atom. So let's say I have sodium. without looking at the periodic table, you need to be able to calculate what the predicted mass will be. So that's gonna be Z times the mass of a proton plus Z times the mass of an electron, because the protons and electrons, if it's neutral, should have the same number, so whatever that Z number is, which is 11. Or you can use Z times the mass of a hydrogen atom, because a hydrogen atom has 1 proton and 1 electron. So you'll be given these values, so these will be on your equation sheet. You just have to know how to apply them. And then you have N times the mass of a neutron. So that will give you your mass of this right there. This comes into play when you're doing like Q value calculations. You can either do it the long way, or you can use the mass deficit or the mass excess.
Mass excess.
Mass excess. So mass excess values will be provided for some questions. Some questions you will have to do it the long way and figure it out that way. So that is, yeah, I think that's where I want to go with that one. And yeah, so mass defect. So what is the mass defect? Knowing like what the mass defect is. Okay, so the mass defect is going to be whatever you find on the periodic table, this mass under here, so it's maybe 23 point yada yada yada, okay, minus that number, okay? So that's gonna be your mass defect. Okay, so you're gonna take the given mass that's on the periodic table and subtract it from its mass number, okay? So this is your mass number, that is your atomic number. Your atomic number is your proton number, okay? So if somebody says atomic number, if I ask for an atomic number, I'm always asking about the proton number, okay? When you're calculating mass defect, you're just taking whatever, you'll have a periodic table, so you're gonna take whatever that number is at the bottom of the periodic table and subtract it from its mass number, and that's its mass defect, okay? Yeah. All right, let's see. Knowing how to convert, did you have a question? Oh, okay. Knowing how to convert between atomic mass number and NeV. Anybody remember what that number is?
2.
Nope, not a 2.
Okay. 2 something.
1 AMU equals, starts with a 9.
924.
Close.
927.
Nope. 1 atomic mass unit is 931.5.
Ooh, I would have gotten there. I really would have gotten there.
931.5 MeV. So when you are calculating like the actual mass or the calculated mass of your given radionuclide, and you need to convert it to MeV, you're gonna take whatever this number is in AMU, and you can convert it to MeV by doing that conversion. Or you can do it on the front end and convert the mass of a proton from AMU to MeV, mass of electron, mass of a neutron, and convert it to MeV, and then calculate. So you can do it either way, they're interchangeable. So mass defect and binding energy. So what is the difference between mass defect and the binding energy? So let's think about when we look at the periodic table, which I have one here. Let's see, probably do. Yeah, here we go. All right, so when we look at the periodic table, we see like underneath here, we have some mass values, right? And if we take this value, like let's say we're looking at platinum, on the periodic table it says 195.1, and we can say that's grams per mole or AMU, whatever. And if we subtract that from its mass number, we'll get a difference, okay? Or if you take this value that's on the periodic table and you compare it to your calculated mass, there's gonna be a difference, okay? And that difference is that energy, if you convert it to MeV, the energy that it took to create that nucleus, okay? So if you guys remember back, this is like probably our first PowerPoint, maybe first or second, where we talk about mass defect and binding energy. They're interchangeable. So basically you take whatever you calculated and you take whatever its actual value is, subtract that, there's gonna be a mass difference, okay? So, for example, I think the example that is in our lecture, we have helium, and this marker sucks, so let me get a different one. There we go. So we have helium, and we can work this one out. So we have Z times the mass of a proton, or we'll just do Z times the mass of a hydrogen atom plus N times the mass of a neutron. So who remembers what the mass of hydrogen?
4 point.
So let's go to our appendix and our textbook. .00, so Z, so we have 2 times 1.0072825 AMU plus N equals the mass number minus proton number. So you have 2 times the mass of a neutron, oops, equals 2 times the mass of a neutron, and that would be 1.008665. Is it 66? Yeah, 665. AMU. All right. So, anybody have a calculator? No? Yes? Maybe?
Yeah.
So 2 times 1.007825 plus 2 times 1.008665. It's gonna be something like
4.0329.
4.0329? Okay, AMU. Okay, now if we look on the periodic table, we see that for helium, it says 4.0, well, it's actually 4.02603. But if we had a better periodic table, the actual one on the periodic table is 4.02603 atomic mass unit. There's a difference between what we should expect the mass to be and what the mass actually is, okay? So the difference between that is the mass defect. Now, how we turn mass defect into binding energy, you multiply by that conversion. So you take the difference between these, you multiply by 931.5, and you will get the the binding energy. And that is the energy it took to make or create that nucleus. Okay? Yep.
I thought mass defect was the number we see on the periodic table, or the difference between the number we see on the periodic table and the 4.
Oh, wait a minute. Yeah, you're right. Hold on. Or maybe I'm wrong. Mass excess, mass defect.
Wait, what did you say?
Okay. Yeah. Okay. Yeah, so this is the mass defect. So probably what I said earlier. What did I say earlier about, what did I say earlier?
You said mass defect and binding energy were interchangeable. and the predicted to use mass excess for something else.
Okay, so I might have said it wrong, but the mass defect is whatever your calculated mass, so your mass of your hydrogen or your mass of your proton and your electron, plus your mass of your neutron, however many you have, that is what your calculated mass is, your calculated atomic mass. Then you look on the periodic table, and there is a difference between that and what's on the periodic table. That's your mass defect. The other one is the, I forgot what we call that. Probably don't need to know it. Oh, maybe that's your mass excess. Yeah, I believe that's the mass excess. See, even I get confused. 60. Okay, yeah, so mass excess, that was the other thing. So it's, the mass excess is how much the atomic mass, so whatever's on the periodic table, differs from the nuclide's mass number. So that would be, this is what's on the periodic table, minus this is your mass excess. Yeah, and you can convert it, in your textbook, it's converted to NeV, okay?
And that's your delta or something.
Yeah, that's what you use, the delta M, the delta sub M. So mass excess is, if you see this, that's mass excess. And it can be whatever, so it would be per helium for that one.
For binding energy, in my notes that we took in class, I have that binding energy is the energy that holds a nucleus together, but you said it was to create.
Yeah, so it's what's holding the nucleus together, but it's also the energy that can, the energy that you need to break it apart.
Okay.
Yeah. So it's just the energy that's keeping the nucleus together, that's the energy that it takes to form the nucleus and or break it apart.
Okay.
Okay, and some of that the difference in that mass is converted to energy, the energy that it took to bring it together, or the energy that you need in order to break it apart.
Okay.
I think in the most recent homework, we had we had to do a calculation, I think that had to do with this, where we used a mass excess instead of the mass. Do you remember it was in the most recent homework? And
Yeah.
I got the same, I used the mass and I got the same answer, when I compared, but like I didn't use those values, and then apparently we were supposed to use the delta NeV squared values, I think.
Was this homework 4?
It could have been.
Not the one that we just turned in, the one before that.
Yeah,
Okay,
yeah.
Let me look at 3.
And I'm just.
But the
'cause I want-
reason that happened, that we were okay using that, is
Yeah.
because when we subtracted the two big numbers,
values,
they equaled 0, so
Yeah.
you're just left with the mass excess.
But-
Okay, so let's see, homework 3. The first question was, it looks like we're calculating the Q value, the threshold.
Oh, Q, that's it.
effective
Yeah.
Coulomb area.
That's it, sorry, so that was something else, okay.
Okay, yeah, so you can use the mass excess, because it would be a lot simpler, or you can calculate, you can do it the wrong way.
I didn't,
You didn't?
and I still got the same values.
Well, yeah, you're gonna get the same values. Yeah, because the mass excess is just a shortcut. It's still, you're still gonna get the same numbers, because, when you're doing this calculation, it's factoring in, if you're doing it the wrong way, it's going to, I don't know how it's gonna factor it in, but you're gonna get the same answer. It's just, if you wanna use less numbers, you use the mass excess value. Or you can calculate the calculated mass and subtract all of those numbers from each other. Well, the products and the reactants. So, I don't know, maybe that's confusing. But either way, I would just use the mass excess values. If you wanna calculate everything out long way, that's fine. Just know what you're using where. As long as your math follows, and I can follow your math, I will say, it's a little difficult sometimes with handwriting and stuff, so, if you could like space it out a little bit, or at least write the equation that you're using down, that will help me figure out what it is you're doing sometimes. Cause a lot of times I'm like searching for things and I'm like, I'm not sure where we're going here. But just so I can follow what you're doing, just write the equation out that you're using. All right. I'm just gonna restart. All right, let me go back here. All right. Okay, chart of the nuclides. Where are certain types of decay likely to occur? So beta minus, beta plus, or positron decay, alpha decay, electron capture, being able to label the parts of the chart of the nuclides where those decays are most likely to happen.
Is it the same question that we had on that midterm review?
Yeah,
Okay.
yeah, but it just might be identifying a different region or
Okay.
labeling them all.
I see.
All right, so stability, which radionuclides are the most stable? I'll give you guys a list of radionuclides and you have to determine which one is the most stable. Sometimes you will have to use multiple ways to determine which one's more stable because they might have all the same N to Z ratio. So if you think it's just N to Z ratio, you have to determine, okay, what else determines stability? And that would be your binding energy per nucleon. So you calculate your binding energy from your mass excess and you divide it by the number of nucleons. Whichever one has the highest binding energy per nucleon is the one that is the most stable. Okay? So you'll be given some choices. You have to do a little bit of math. Yep.
Is the way you just said, is that like a surefire way?
Yeah, so the shortcut is, okay, we know stability is, it has to have a favorable N to Z ratio. So the closer N to Z ratio is to 1, we consider it stable, right? Well, if you have a whole bunch of radionuclides that have an N to Z ratio that are around 1 or a little bit over 1, but one's 1.01 and one's 1.012, you know, they're all kind of around the same. Then you want to look at the binding energy per nucleon, okay? Because that determines like how unstable your nucleus is, the binding energy of each nucleon to each other. So you take that calculated mass excess, turn it into binding energy by multiplying it by our conversion factor here, and then distributing that between all the nucleons. So you divide it by the mass number, and whichever one is the highest will be your most stable atom. Let's see, is there anything else in that section? Chart of the nuclides. Yeah, just knowing what the chart of nuclides tells you and knowing what regions, probably magic numbers. That's another indicator of stability. So if you have magic numbers in your nucleus, that's another way to determine stability. Doubly magic. So if you have both proton number and neutron number in your nucleus as a magic number, it's doubly magic. Those are very, very stable. Let's see. Knowing how to write decay equations. So alpha decay, beta minus, beta plus, electron capture. And now we have fission. So that's another type of decay. So I think we had a neutron-induced fission for our last homework. We had to write down the generic equation for neutron-induced fission. Yeah. So it'll be something like that. So you have to know how to write those out. The decay diagram. So decay diagrams, you're gonna have to calculate Q values. If you have an alpha decay, so it could be a combo question where you have to write out the decay equation for alpha decay, calculate the Q value, and then the energy of the alpha particle and how far it travels in air. So that's probably a big one.
Wait, decay equation for alpha decay, and
Yeah.
then what? Calculate Q?
Yeah, calculate the Q value for that reaction, calculate the energy of the alpha particle, and then calculate how far the alpha particle travels in the air. Now, you will be given an equation sheet. You just have to know which equation to use for what, okay? So do not make up equations that are not on the sheet.
I did that last time, it doesn't work.
Just use the equations that are provided. We're not doing calculus here. All right, calculating specific activity. We know it's activity per unit mass. So if you are given, well, first let me backtrack. So calculating activity. Activity is lambda n, so we have a couple of different ways to talk about activity. Are you guys done with this? All right, so activity. All right. Let's see. Oh yeah, here we go. All right, so here is our basic activity equation, right? So we have our decay constant, which is given in units of inverse time, times n, which is what? Number of atoms, right. Okay, so if you are given, calculate the activity of 0.01 milligrams of plutonium-238. And you're given the decay constant of whatever it is. You'll take that decay constant, which is the natural log of 2, over its half-life. And if this is an actual question, I will give you the half-life or some means of finding it, okay? And then you have to calculate how many atoms of plutonium are in 0.01 milligrams. So you take your 0.01 milligrams, you can convert that to grams, 1,000 milligrams in a gram, and then 238 grams per mole, and then you use Avogadro's number to get your atoms, and then you multiply the two together, and that should give you your activity in some sort of atoms per unit time, okay? So what that's telling you is how many atoms are decaying per unit time, okay? So that's what activity is telling you. So if you're looking at specific activity and you determine activity, you just go back and divide it by how many grams you have. So it'll be becquerel or curie per gram. Do we know how to convert between becquerel and curie?
Yes.
Yes. So curies, here's a clue. If a curie is some really huge number, you probably did it wrong, okay? So curies, in the United States, we like to deal with curies because they make us feel safe. But becquerel is more realistic in terms of the scale of what's happening with the atoms. So if the becquerel, if your number is like times 10 to the 20 something and it's in curies, you probably did something wrong there, okay? It's probably gonna be becquerel. So becquerel is always gonna be like the larger number. And the conversion, does anybody remember the conversion? 3.7 times 10 to the 10 becquerel is 1 curie, okay? 3.7 times 10 to the 10 becquerel is 1 curie. So remember, the curie is always the smaller number, the becquerel is always the larger number, okay? All right, let's see. Oh, another one that I like to put on there is I give you a chunk or section of the chart of the nuclides, and you have to name isotope, an isotone, an isobar, one of those things. So we know an isotope, same proton number, you have P, isotone, same neutron number, isobar, same of both, B, so that mass number is the same. Yeah, so, yeah. Also from the chart of the nuclides, you might have some sort of question where you have to identify the mode of decay and just write out the generic equation. So I'll give you a little slice of the chart of nuclides, and ask you to write out the decay equation for actinium-227, okay? Also, along with that, that might have some sort of branched decay going on with it, so it can decay maybe via beta minus, or it can decay via positron or electron capture. So you'll have to determine what the net rate of production or decay for branch decay. So remember, we have marker down here.
Do you want, I have,
Oh, no, I'm good, we got it. And I have like 5 up here that I obviously been collecting. So, branch decay. So we have our parent radionuclide, and it can decay via one way. So we'll call this B, and we'll call this C. Okay, so you have your parent, whoops, sorry. So you have your parent decaying in 2 different ways to their progeny, B and C. And for A, when it decays to B, there is a net rate of production. So remember, activity is equal to lambda n, but if you have branch decay, you want to figure out what is the activity for just B, okay? So if I want to determine what the activity is for just B, what is decaying? A is decaying, right? So A is decaying, so that would mean, this is not Avogadro's number, we like to use the same letters all the time. So you're looking at the atoms of A, that's decaying, but it's decaying into B, so you have to use the decay constant for B. So if you want to look at the net rate of production for B, you're going to have the decay constant for B and what is decaying, which is A, okay? Same thing for the other side, except for now you have a different decay constant. You have the C decay constant, but A is still decaying into it, okay? Now if we want to look at the total decay constant for A, we have to say that the decay constant for A is equal to the decay constant of each of its progeny. And that could go on for n number of however many ways it decays, okay? Now, if we want to look at the net rate of B or C, let's say B and or C is also decaying. So you're producing it, but it's decaying at the same time, okay? We're still going to use this equation, but now we have to look at what's decaying. Now we're looking at B is decaying. All right, so if A is producing it, we're looking at A decaying. If B is also decaying, we have to look at what's happening with B. So we look at the number of atoms of B that are decaying based off of that decay constant, okay? So if you want to look at the net rate, and this is going to be negative for that because it's decaying away. So dNB dt would be equal to this minus that. So this is your production term. That's something you will probably have to know. Production term. And this is your decay term. Okay? Just like if A was decaying, A would be, this is the decay term for A. So you're just making sure that you remember which one is what. All right, and just making sure you choose the right equation. Oh yes, labeling secular, transient, and no equilibrium. Okay, remember that equilibrium for secular equilibrium is usually reached after 7 half-lives. So if you So we're looking at activity. is time, it can be in daughter half-lives, or just time, period, so, time and half-lives. So this is for secular. So your parent is usually, has a very, very, very long half-life, okay? So over time, you're not gonna see it decay. So its activity is gonna remain basically the same, okay? But it is decaying a little bit because it's got a decay constant, right? So that means that the daughter or the progeny that's growing in is growing in a little bit, maybe I'll make lines. Over time, okay? So this is the progeny or your daughter, okay? So over time, your daughter is growing in. Right about the time when the activity of the progeny and the activity of the parent is the same, that is about 7 half-lives, okay? So it takes about 7 half-lives for the progeny to reach the activity of the parent. Now, if the parent half-life is like 5,730 years, that's gonna be a long time before the daughter reaches equilibrium, okay? So then the total activity, so this is also, you have to include the total activity. I'm trying to find a different color. So then you have to include the total, which is just this activity plus that activity, okay? Secular, equilibrium, you have to know transient and no equilibrium. So for secular equilibrium, the half-life of the parent is way greater than the half-life of the progeny, okay? Transient, the half-life of the parent is still greater than the half-life of the progeny, but not by like 5,330 years. It's usually very close, okay? And so that will look a little different. No equilibrium, the half-life of the progeny is greater than the half-life of the parent, okay? So there's no equilibrium there. So the parent dies off really quickly, the progeny grows in, then decays away. All right. Okay, yeah, so I went over that, decay diagrams. Also, decay diagram, if I give you a decay diagram, you need to be able to tell me what type of decay is happening, okay? So if you are losing protons, a proton is turning into a neutron, the decay diagram should go down into the left, right? Because you're losing protons. You have to know what type of decay that is. Also, if you see a decay diagram whose Q value, let's say you have a decay diagram where you don't know if it's beta plus or electron capture. This is gonna, I'll tell you this is gonna be on there. So if you have a decay diagram and you have to determine if it's positron decay or electron capture, what is gonna be like the dead giveaway? Yes, the amount of energy. What kind of, like, what's that number?
2.
Nope. Nope.
Bigger, it's like
Nope, it's not bigger.
small, it's, okay.
So positron decay. So let's think about what a positron, where it's, what is, what, let me see if I can say it without saying it.
What's positive?
Well, no, that's not what I'm getting at. All right, so positron decay and electron capture happen at 2 different energies. There's a minimum energy for positron decay to happen. And it has something to do with annihilation. Okay? So just think about that. If you see that decay diagram and it's asking you to determine whether this is electron capture or positron decay, one happens at a higher energy than the other. And so that is like the dead giveaway. So you want to look at the Q value and determine if that Q value, the total energy of the reaction, is greater than this number, and if it is, it's most likely positron decay. If not, then it's the other. I just gave it away, okay? All right. Let's see. Oh yeah, interactions of radiation with matter. Linear energy transfer of the different type of particles. So alpha particles, beta particles, gammas, neutrons, So you have to know the LET, which is gonna have a larger linear energy transfer, okay? So if we think about each term linear, so we're thinking about linear, obviously linear is a line. So let's say you have your, whatever is decaying, okay, and it's passing through some matter, blah, blah, blah. As it's traveling through this matter, it's going to lose some energy, okay? Because it's going to interact with matter. And we'll talk about the ways it interacts with matter. So let's say this is an alpha particle, and then we'll have like a beta minus, and then we'll have a gamma, okay? So they're all going through this matter of some thickness. Doesn't really matter what the thickness is. We know that alphas are large, they're kind of bulky, they usually have a lot of energy. So since they don't travel far, they probably make it a few centimeters into whatever surface it's like your skin. Your skin can block alpha particles. A piece of paper can block alpha particles. So it doesn't make it too far. So if this has some energy and it only goes this far, it's going to have some LET associated with it, some linear energy transfer that it's given into the material or the matter over some distance, right? Beta minus particles are lighter, it's basically an electron. They're going to travel a little bit further into the material. These have some energy, so it's traveled this far, it's going to have some LET or some linear energy transfer associated with it. Gammas are basically just energy, weightless almost. So they're gonna possibly travel all the way through, okay? So when we're looking at, let's say just these three, for example, out of the three of these, which would have the higher linear energy transfer into the matter?
Probably alpha.
Yeah, the alpha particle, right? Because an alpha particle it's gonna give up all of its energy in a very short amount of space. So if we looked at this same amount of space for a beta, that beta is still gonna have some energy left to travel. So the linear energy transfer for that same amount of distance is gonna be lower for a beta particle than it is for an alpha particle. A gamma is probably most likely gonna go right through or get attenuated somewhere down the line. So its LET is gonna be pretty low for interactions of radiation with matter. Let's see. Oh, my favorite. Auger's. Please, please, please. Know where Auger's come from. All right. So if we are talking about, so let's go back. Interactions of radiation matter. There are different ways that things can interact with matter, okay? They can either interact or they won't, okay? Now, if they do interact, they are absorbed, they're scattered, okay? So if we're talking about photons, or they're, scattered. So if we're talking about photons or gammas, so gamma interactions, we have three different kinds. So we have this little graph here. Remember, so this is like the photon energy, and this is the probability of interaction, so kind of like the cross section. So for low energy photons interacting with matter, what is the possible interaction it can have?
Compton.
No, well, yes, it can interact via Compton scattering, which kind of covers that little area there, but what goes here?
Pair.
Photo.
Photo.
Photoelectric effect, okay? Pair production. When we're talking about pair production, you're producing two things, right? In order to produce those two things, you have to have a certain amount of energy, kind of tied back to our decay diagram thing. So you have to have a certain amount of energy. So you have to have, pair production has to have a lot of energy in order to produce a positron and beta minus particle of a certain amount of energy. So you have to have a certain amount of energy coming from your photon interacting with matter in order to do pair production. So, photoelectric effect. Does photoelectric effect happen in the outer shell or inner shell electrons? No! No. Photoelectric effect. Photoelectric effect is inner shell electrons. And why? Because they produce these great things called OJs. I just like that
That's
word.
why you're mad at me.
Yeah. All right. So photoelectric effect. So you have your nucleus here. You have, because this is exactly what an atom looks like. Just kidding. And then let's see, 1, 2, 3, 4, and then you have some more on the outside. Let's see, 1, 2, 3. 1, 2, 3. Either way, they're supposed to be 6, 8. All right, so you have your photon, or you have your gamma, whatever. It's going to interact with an inner shell electron, okay? It's going to give it enough energy for this electron. Now there's a vacancy there. That electron goes out. It's bye-bye, okay? Gives it enough energy to do that. All of the energy of that photon is absorbed by that electron, giving it enough energy to be ejected from the atom, plus some energy to move around, okay? So this creates a hole. So these other electrons on the outer shell, they're like, oh, hey, there's a new apartment opening, I'm gonna move in. So they want to move down, okay? They want to occupy a lower shell, right? So in doing so, they're gonna give off some energy in the form of a what?
X-ray.
X-ray. So this right here is an X-ray, okay? So this energy that comes off from the dropping down of electron to a lower shell gives off an X-ray. So this X-ray could exit the atom and you'll get X-rays, or on its way out, it could hit another electron, giving it energy, making a vacancy, and it is ejected as our OJ.
The X-ray hits it, right?
Yeah,
The auger.
the auger. That's what I thought it was, just apparently OJ. So now there's also other things that can happen. That OJ can hit another electron on its way out, creating secondary electrons. We're not going to go into all that. Just please know where OJs come from. You can draw a picture, but knowing that it happens via photoelectric effect, inner shell electron. So Compton scattering happens
Outer shell.
in outer shell electron. Okay, so when we have Compton scattering, you have an incoming photon, it interacts with an outer shell electron, and I probably will have to draw again. So I'm just gonna erase this whole thing. You have your nucleus, boom. We're just gonna do this here. So you have your photon, your incident photon. It's going to interact with this electron at some angle, okay? And then this electron is going to be ejected. So now you have your ejected electron, and then your photon will get scattered, the Compton scattering, at some angle theta. So now you have your, so you're able to calculate the energy of your scattered, a Compton electron, so this would be your Compton electron, and this would be your scattered photon. Okay? There is an equation that will be provided for you to calculate that. Obviously, you have to know what the max scattering angle would be and what would be the maximum energy provided to the electron at that max scattering angle.
What is the SC and
That's a
C?
scattered photon. Yeah. Usually when the equation will say SC. And then Compton electron will be C. Let's see. I think I'll get rid of that question there. Okay, so earlier we were talking about activity. So activity at an instantaneous point is given by lambda n. And we want to know activity after some time. We have our equation a sub t equals a sub naught e to the minus lambda t. So that's for activity. Now, if we're talking about a monoenergetic beam of photons, we have a similar equation. It's the intensity that reaches our eyes, reaches our detector, you know, whatever our detector is. So this is the intensity that reaches the detector is equal to the initial intensity to E minus mu x. Does anybody remember what mu is?
Property of the material.
Yes, it is a property of the material, but what is it called?
Linear attenuation.
Linear attenuation coefficient, okay? So if we think about each word of that, linear attenuation, and it's a coefficient. So how much that particular beam or energy is being reduced per unit length, okay? And this is multiplied by x, which is the thickness. So either whatever length will cancel out, and you should just get an intensity, okay? So if you're given a monoenergetic beam, it starts out as 5,000, it goes through 2 centimeters of lead. Will you still use this equation? And if you wanna calculate how much it is attenuated going through lead? Okay, so this is the linear attenuation coefficient. Then you also have a mass attenuation coefficient. Mass attenuation coefficient. And then you also have an atomic attenuation coefficient. So if you want to know just overall per unit length of whatever it is, you want to use your linear attenuation coefficient if you're not told what it is, okay? If you're given mass or like it's lead, usually I will provide you with the density, which is in grams per cubic centimeter. Your mass attenuation coefficient is going to be given usually in centimeters squared per gram. So just like our decay constant, which is in inverse time, our linear attenuation coefficient or any of our attenuation coefficients is going to be in inverse length, okay? Because you're multiplying it by some sort of thickness, which is a length. So if you are given something where you're asked to calculate the attenuation in some sort of property of a substance, like lead or tungsten, and you're given the density, then you want to use the mass attenuation coefficient, because now it's asking about a specific type of material, okay? So if I don't give you the material, use the linear attenuation coefficient. If I say it's going from lead or tungsten or plastic, then you want to use the mass attenuation coefficient. The atomic attenuation coefficient, we don't really use that much. It's basically how much those photons are being attenuated per atom, okay? That's if you wanna go down real small, like how much each atom is attenuating these photons. Then the mass attenuation coefficient is, I wanna know like how much lead is attenuating it, or how much plastic is attenuating it. Linear attenuation coefficient doesn't care what it is. It's just how much per unit length of whatever substance is gonna attenuate that. Let's see. I might get rid of that one. Also, homework problems are all fair game too. So if there are homework problems that you might have not understood, like, let me know and we can go over them next class. Because we're only halfway through this old final. We only have like 20 minutes left. All right. Inner shell electrons. Okay, maximum sphere removal. Oh, yeah. Exposure. Exposure equation. And using 10th value layers and half value layers to determine the exposure for someone. So you might be given, you might have to calculate what thickness of material would lower a person's exposure to half of what their weekly exposure was. So knowing the exposure equation, and then there might possibly either that exposure equation or shielding equation. Okay, so I think that was on the last homework. Maybe not homework 4, but homework 3, where you guys did a shielding equation. Gas amplification curve, and knowing what type of instrument to use for detecting which type of material or a decay. So if I'm looking to discriminate between alphas and betas, what section of the gas amplification curve am I going to look at? So we have something like intensity. Is that intensity? It is.
What is this called?
This is the gas amplification curve. I'm just trying to get, oh, pulse height, sorry. Or intensity, either way. So this is like pulse height on your instrument, and this is like the voltage. So at very low voltages, you have, let's see. So there's 4 regions that you'll have to know. Whatever. All right. So you'll start off in ion chamber region. So at very low voltages, that means in your detector, your whatever's interacting on the inside of that gas-filled detector is going to produce a certain number of ions. It doesn't have enough energy to actually discriminate between 2 different things, so it's just going to make enough energy to give a signal, okay? So usually you'll have alphas and betas. Okay, so very low energy, not going to get a good signal, it's very low because you don't have a lot of voltage being applied. Next region, you have your proportional region. So here in this region, you have enough of a difference between your alpha signal and your beta signal to differentiate between your alphas and your betas, okay? Then this next region, you have your Geiger-Müller region, and here you can't really discriminate between your alphas and betas. It's gonna produce just one signal, okay? That's gonna be, I don't wanna say proportional, but you usually get good readouts from GM detectors. Then after here, you have continuous discharge. It doesn't matter what kind of energy is applied, it's gonna basically like blow out your whole detector, not blow it out, but it's gonna overwhelm it. You're not gonna get any reliable readings from here. No one uses or even makes continuous discharge instruments, because there's no point, because you're not gonna get a reliable reading from it. All right, so knowing the regions of the gas amplification curve, the ion chamber, proportional region, Geiger-Müller, and continuous discharge.
For Geiger-Müller, do we label that and we put GM, is that not enough?
Yeah, GM is fine.
Okay.
So if you have a gamma emitter, would this apply? Would you look at a gas amplification curve for a gamma emitter?
No.
Probably not. What type of instrument would you want to use? A scintillation detector and or a semiconductor detector, okay? So semiconductor detectors or scintillation detectors work well for betas. So betas and alphas you can also use. Usually you're putting it in some sort of cocktail, like a scintillation cocktail, where it has some sort of I can never say this word right, fluor, something that lights up. When,
I had the weirdest dream 2 nights ago where radioactive cocktail, but it was a latte. It was a radioactive latte.
Okay. Well, if you ever run into a radioactive latte, don't drink it.
Yeah, no.
Okay?
You're like, God, no.
No, I don't know. Hopefully no one's trying that.
It's just a dream, it's
You
just a
turn into
dream.
the Starbucks lady with the fish legs.
I want the green one, please.
No, you can't get superpowers from drinking something like that. You'll die. Okay? Death is imminent for that. Yeah, that's your superpower, is early death.
My grandma lived to be 107. She lived through World War II.
Did she drink?
No, but she like walked through gas all the time.
Oh.
Yeah.
Well, all right, maybe she did have superpowers. All right, so betas and alphas you can use scintillation detectors on as well, but gammas you want to use, and betas you want to use a scintillation detector and or a semiconductor detector, okay? Because gammas basically travel through anything. You want something that's going to try to attenuate those gammas and get a reading off of it. Yeah, so 3 ways gammas interact with matter. Knowing what a gamma spectrum, labeling the parts of the gamma spectrum, okay? So, whenever we're looking at the gamma spectrum, and I'm going to draw a really, really horrible drawing, but hopefully you guys get the gist of it. Alright, so you have your little I might be missing one thing in there. Oh, no, I'm not. Okay, great. All right, so we're looking at a gamma spectrum. So we have to know the different ways that gammas interact with matter. So this is like the counts and the activity, and this is your energy. All right, so, sorry, AED apparently on this picture. So I need to know if you can label this peak, that peak, this right here, and these. This is gonna be on the exam. So you have to be able to label these peaks. So if we think about the 3 ways that gammas interact with matter, remember we have a photoelectric effect, we have Compton scattering, and we have pair production. So in photoelectric effect, we are interacting with the outer shell. Inner shell. All right. So we're interacting with the inner shell electrons, So we are also going to be producing X-rays, right? Because you have that electron dropping down into that lower shell. So this would be a product of the photoelectric. You don't have to label the photoelectric effect or anything, but just knowing the ways they interact with matter will help you label this, okay?
Oh, that's what you weren't looking for, like the name of the curve, okay.
Well, yeah. So yeah, what is this peak? This is an X-ray peak. Usually X-rays, because it's just an electron dropping down from one shell to another, the energy is gonna be really low, okay? But the signal, the amount of counts you get might be high, but the energy is really low. Yeah?
Would a word be called, also called the photoelectric peak?
Yeah, the photo peak, so this is the photo peak right here. And this is also the photoelectric effect, okay? Okay, so if we have a gamma interacting via the photoelectric effect, remember it interacts with an inner shell electron, giving it all of its energy, okay? So this represents the total energy of that photon. Remember, there's lots of them happening at the same time. So the total energy of your photon, let's say your photon was a 200 keV photon. That means this photo peak would be right here at 200 keV. But because it's interacting via the photoelectric effect, you are ejecting that electron and another one is dropping down. It's gonna emit some X-rays, okay? So these two are photoelectric effect. What's gonna happen with photoelectric effect, okay? All right, so next you have Compton scattering. So Compton scattering, you're interacting with the inner shell electron? Outer shell, all right, outer shell electron. So what's gonna happen with Compton scattering? You have, in that other picture I drew, you have that photon interacting or scattering at some angle. Depending on the angle, you get different energies of your scattered photon, okay? And so this is representative of all those different energies of the scattered photon, okay? So if it interacts at the maximum scattering angle, you're gonna get that photon scattering back. So this is a backscatter peak. And this is Compton scattering. Then you're gonna have the maximum energy that a photon can have. So it'll just like skim off of that electron. It'll still retain most of its energy. So this is called the Compton edge. So that's why the energy is a little bit higher. And then this represents all the other scattering angles that could happen and the energies that come with that. So this is called the Compton continuum. Okay? And yeah, so knowing the three ways they interact. Now pair production is not on here, okay? So remember pair production, what's happening with pair production?
Not a lot of energy.
Get together and like.
Your photon has a lot of energy. It has to have at least what MeV? This is like the number we've been sticking around.
1.022.
Okay, think about that. It has to have at least 1.022. So you have a photon with at least 1.022 MeV. It's going to interact or come close to, I took my picture down, with the nucleus of an atom, and it's going to create a positron and an electron. So now thinking back to the beginning of this review when I talked about a decay diagram, and you have to determine whether or not it's positron decay or electron capture, if the total energy of the reaction is at least 1.022, you know it's going to be positron decay. If it's anything less than that, it is electron capture, okay? It can still be positron, but it has to be at least 1.022, okay? So you won't see, if you're given this particular one and you have to label it, pair production may or may not be on there. But if you are looking at pair production, I'll draw a little miniature version. You have your photo peak here. You have your, yeah. So you have either one, so you have a positron and your electron, right? You can either have both of them escape, or you can, wait, I might have that the other way around. You either can have both of them escape, or you can only have one of them escape. So you have a single escape peak, and you have a double escape peak. And this is your photo peak. But remember, that has to be greater than 1.022 MeV, okay? So these will either happen at 0.511 keV, each of your positron and your electron will have at least 0.511 MeV. Now, if your photon comes in with 2 MeV, you could have a positron and an electron with more than 0.511 MeV each, okay? All right. So if asked which peak corresponds to the energy of the photon, that would be your photo peak. If you're asked which one is your backscatter peak, you're looking at that little hump right here. And if you're asked, like, what are all the energies that could happen from Compton scattering, where is that represented? That's your Compton continuum. All right. Have you guys had enough? We've got like 5 minutes left. We haven't, well, we made it a little past halfway. So Thursday we'll take it back out and we may go over like some homework problems. But there are a few that you will see, like literally gave you the answer. So, any questions? Any questions? You can always email me, text me, whatever. Yeah, just remember we're having our exam in here. Did I go over this with you? Or, oh, no, you walked in. All right, so December 9th, our exam is in here. We only have 2 more